We're going to continuing lecturing here, chapter 3. Last time we got into bonding, and we really talked about two types of bonding last time. We talked about ionic bonding. And ionic bonding is always, as we talked about, really between a metal and a non-metal. And because of those sort of periodic trends that we talked about, what we always will see happen is the metal will typically give up those electrons over to the non-metal. The result of that is we're going to get a cation that's formed, which is going to make a positive charge. And our non-metal will accept those electrons and make a anion, which is negatively charged. Remember that when we have an ionic compound, there really is no sharing of electrons that are happening. It is clearly just the attraction between the positive and negative ion in this particular case. We could show that using Lewis dot symbols that we talked about, like, for example, lithium, which has one valence electron. Remember that the number of valence electrons equals the group number 1s2, 2s1. That would be its valence electron. Plus, like we talked about, fluorine, which is group 7, has 7 valence electrons, 1s2, 2s2, 2p5 in that case there. And what's going to happen here is the lithium is going to transfer that electron over to the fluorine, and that is what's going to cause our ions to form here. We're going to make a lithium that will now become positively charged. We will then have that fluorine that picks up the electron and becomes negatively charged. And the result of that is, again, it gives up its valence electron there, ends up at 1s2. Its fluorine accepts the electron right there, 1s2, 2s2, 2p6. Once again, as we talked about, really the whole purpose of bonding is for everybody to achieve noble gas configuration, which they do. Our lithium becomes neon configuration. Our fluoride there becomes helium's configuration. And our fluoride there gets to neon's configuration. That, again, as I mentioned, is the purpose of all bonding, is to basically achieve noble gas configuration. We then got into sort of covalent bonding, which is different. It is typically between two nonmetals. And again, because these two nonmetals are basically in the same spot on the periodic table, they have very similar periodic trends, which means neither one of them, for example, wants to give away their electrons. So the best that they could do is basically share electrons. So we get some type of sharing of electrons that happen here. And that, again, is different than ionic bonding, where there is no sharing of electrons. It is that electrostatic attraction that holds that together. The sharing may be equal or unequal sharing, and really it is that electronegativity, as we, I think, finished up upon talking about, which sort of helps us determine whether or not the electrons will be shared equally or unequally. The idea here, again, is we do get bond formation in the case, for example, like we talked about with, say, two hydrogens coming together because they have identical periodic trends. They will decide to share those electrons between the two. The result of that, again, is those electrons will count for both atoms in the bond, and in this case would give this hydrogen 2 electrons and this hydrogen 2 electrons, which will make it basically happy in that sense as it gets to helium's configuration. Same thing we saw with fluorine. Again, when we get two fluorines together, they will also share those electrons, and at this point, we will get something that looks like this. Again, those electrons in the middle will count for both of the fluorines, giving both fluorines 8 electrons, which also moves it to noble gas configuration and makes it really happy. Remember that those bonding electrons, which are the ones that form the bond, can also be represented with a line. And our non-bonding electrons, or lone pairs, are usually represented here with dots. We got to the point of talking about really how these electrons are going to be shared equally. In the case of fluorine and fluorine, or even hydrogen and hydrogen, because they are the same element, they will have identically the same electronegativity value, which means that they will be sharing the electrons equally. There'll be a same amount of pull towards both nucleuses in this case. And that will create what we refer to as one type of covalent bond, which is a nonpolar covalent bond. And a nonpolar covalent bond is basically where we have equal sharing of electrons. The result of that is it creates a bond, for example, that is essentially neutral. There is no side that is more positive, there's no side that's more negative, because we have equal sharing of electrons. Different than that is our hydrogen, say, I think is what we were looking at the very end there. When these two guys get together, we now have still sharing of electrons. And in this case, once again, the sharing of electrons between the fluorine and the hydrogen will allow each of these guys to really max out at where they need to be. But in this case, fluorine is definitely a lot more electronegative than hydrogen. It is the most electronegative element you could have. And that means that all the electrons will really be heading towards the fluorine side of the bond. And that creates a separation of charge that occurs in this bond. And the fluorine in this example becomes partially negative. The hydrogen becomes partially positive, which once again we can display using a dipole arrow. This arrow, again, always points to the more negative side. And once again, the back part that kind of makes like a plus sign is always to the more positive side of the bond in this particular case. This type of bond where we have unequal sharing of electrons is what is really referred to as a polar bond, or really a polar covalent bond. But again, most people do leave the kind of covalent part of it off, and it is unequal sharing of electrons. Again, the result of this type of bond is it does give us sort of a separation of charge that occurs, because the electrons are hanging out a lot closer to the fluorine in this case versus the hydrogen. As I think we touched upon last time before we finished, the idea here is they are partially positive and partially negative charges, because they are still being shared. So we haven't had a full transfer of those electrons. So it is only a partial positive charge, a partial negative charge. Um, we don't get the full positive charge or full negative charge like we see in an ionic bond. And that's because, again, in an ionic bond, we get the full transfer of those electrons. So that's why we get a full positive and full negative charge. Any questions on any of that stuff we talked about last time? Yes, sir. Yeah. Y- Yeah. So we're going to talk about this in this sort of chapter and the next chapter as well. But there's really two places where that arrow is, for example, used. And if we take your example that you asked about, which is water, the two ways that this sort of dipole arrow is really used is to basically describe two things. It can describe, like we do here, which is oftentimes referred to as the bond polarity. And that is simply, how the electrons are going to be shared between just two atoms, not the entire molecule, just between two atoms. So for example, here with the water example, oxygen is more electronegative than hydrogen. So we could draw two bond dipole arrows, and they would be heading towards the oxygen in this case, to indicate that the oxygen side of the bond in each of these cases between the oxygen and hydrogen is going to be more partially negative than the hydrogen side. And that would indicate that there are polar bonds within, like, the water molecule. There's a second use of that arrow, which is really about molecular polarity. Polarity. And molecular polarity actually, and we'll talk about it actually in chapter 4, but molecular polarity takes into account the entire molecule as a whole. and all the bonds that are present within that molecule. And is the entire molecule as a whole going to be sharing the electrons with all their bonds equally or unequally? And if it's unequally, it'll mean that there will be a part of a molecule that's going to be more negative because the electrons are kind of going in that direction versus the other part, which makes the entire molecule have a positive side and negative side. It oddly is the same arrow that is used to represent molecular polarity. And in the case of water, it actually would run straight up the middle there, where the oxygen side of water is actually more negative and the hydrogen side is more positive. This arrow, though, when you use it for molecular polarity, as we'll talk about, actually is what is sometimes referred to as a dipole moment. And it represents that the molecule as a whole has some overall unequal sharing of electrons. And that's what makes something like water polar. It basically, because of the unequal sharing of electrons within the bonds, and also because of its geometry, it kind of sends all the electrons migrating towards the oxygen side of it. And that means the hydrogen side of it is actually electron deficient. And overall, when you look at a water molecule, the oxygen side is more negative and the hydrogen side is more positive. So there's kind of two applications of that arrow. And when we look at just between two atoms within a single bond, whatever bond it may be, we really look at electronegativity and bond polarity and draw those arrows. When we're looking at the entire molecule as a whole, that's when we would look at, a few other things you might have to look at in that case. But sometimes it's confusing because the dipole moment and those bond, they're all basically the same arrows and they're used for those two things. So there really is sort of two types of polarity that we talk about when we're doing bonding. And again, one's bond polarity and one's like the entire molecule as a whole. Is it going to be a polar molecule or not? Yeah. And again, we'll get more into a lot of that in the next chapter as well. Other questions? Okay. So we were talking about this last time, and again, we get this separation and charge. So just to sort of review, you could think of the different types of bonding that we've been talking about. Sort of at one extreme, we have our ionic bond, which, as I mentioned a second ago, is our metal and non-metal. And here again, we're going to get that complete transfer of electrons. No sharing. And that example would be, again, something like sodium chloride. Again, the sodium is going to lay up its electrons to the chlorine. On the other side of the extreme, we have really a nonpolar covalent bond, which is between two nonmetals. It is sharing of electrons, and here it is going to be equal sharing of electrons. Again, resulted in really kind of like a neutral bond, if you will. So some examples that we saw there, again, our F2 bond, our not HF, but our H2 bond as well. And sort of in the middle of those two types of bonding, we have our polar covalent bond, or just our polar bond. And those are also between two nonmetals. And that is unequal sharing of electrons. That's going to result again in our separation of charge that's going to happen. And obviously what we just talked about there, the HF is going to be an example. So again, on one end of the extreme, we're going to get that transfer of electrons. The other end of the extreme, we're going to have nice equal sharing of electrons. And again, in the middle, we're going to have kind of the middle of that. Not so much unequal sharing that they get transferred, but not perfect equal sharing either. So some really unequal sharing that's occurring. Any questions on that there? So what is really, again, the really overwhelmingly important thing that helps us decide when we look at a bond between two atoms, how those electrons are going to be shared? That is electronegativity. And that is the ability basically of an atom to draw electrons towards itself, like we talked about. Again, it increases as you go this way. It decreases as you go this way. Remember that fluorine is our most electronegative element that you could have. Again, that's as far up and to the right as you could go. Like a weird blinding happening right about now. Maybe that will work. Or maybe I'll break the place. I'm not sure. Let's see. There it is. Oh, that's refreshing. All right. So I can actually see. All right. So again, up and to the right on the periodic table, there is our noble gases, which again are chemically inert. They're not really looking to do anything. Again, everybody's looking to become like them. So remember, electronegativity is related to the electron affinity, which is the energy change that occurs when an atom gains an electron, and the ionization energy, which is the energy required to remove an electron from an atom. So fluorine has very high electron affinity and has a high ionization energy, so it has high electronegativity, while sodium, again, has basically low of both of those things, which means it's not going to really want to gain electrons. So there is a sort of calculation that you can use for electronegativity to help you decide whether or not, if you put these two sort of atoms together, how they will share electrons. And Pauling came up with this sort of system. It's a 0 to 4 system. 4 is the most electronegative you could be. 0 is pretty much not so much. Pretty much not very electronegative at all, for example. So you could calculate what is sometimes referred to as the change in electronegativity value, delta En. And you basically would look at the table, find the electronegativity values for the two elements that are involved in the bond, and you would basically try to decide, what type of bond you have. So in general, if you calculate the electronegativity value, you get a value from 0 to 0.4, it is considered a nonpolar bond. And that's a nonpolar covalent bond. That would be considered equal sharing of electrons. If you actually get a value of 0, that is still a nonpolar covalent bond, but that also is that pure covalent bond that we talked about, I think, last time. That's like as perfect equal sharing as you could get. So you kind of get like a perfect 0. That's sometimes referred to as a pure covalent bond. It's still nonpolar, but it's just a distinction sometimes people will make. If you're above 0.4, which I guess would be 0.5, to below 2, that's going to be some type of polar covalent bond. So you're going to get some unequal sharing of electrons that's going to happen. If you're typically above 2, and not in all cases, but if you're typically above 2, you're going to get a transfer of electrons, and usually that's going to be an ionic bond. Here's the deal with that one. You frankly don't even really need it. There are some exceptions to that. All you need to know for an ionic bond, like we've been talking about, is I have a metal, I have a non-metal, I have an ionic bond. I should just move on with my life. Pretty much, you don't even really need the electronegativity values or anything like that. So you would subtract the two values that you find in the table. You take the larger minus the smaller, so you get a positive number when you do it, and you can help do that. So obviously here's a table of electronegativity values. You can see upper right here, we have our fluorine, which is the most. So for example, if we take a look at a few that we just talked about, which is sodium chloride, we had our HF, and we had our, we'll go with FF bond, right? So for example, if I look on the table here for sodium, that is an electronegativity value of 0.9. I look at chlorine, that is a value of 3. I could calculate the difference in electronegativity by taking 3 minus 0.9. That's going to give me a 2.1. That is above 2, and that means that I should expect this to be ionic. Once again, you really don't actually even need to do that calculation because that's a metal and a non-metal, and you know it's going to be ionic anyway, so you actually don't even need the numbers. you will be right pretty much all the time if you just put ionic for that guy. Now, if we go to fluorine and fluorine here, obviously fluorine there is 4 and fluorine is 4, which means when I take the difference in electronegativity, I got a 4 minus 4, no calculator needed, hopefully. That is a 0, and that definitely is going to be a nonpolar bond. And this would also be classified really as one of those pure covalent bond. That again, it's as equal of sharing as you could get, right? You got basically perfect 0 difference between them. If we take a look at our HF, once again, hydrogen here is 2.1. Fluorine is 4, not 40, but 4. It's kind of like 40, I suppose. And if we do a difference in electronegativity, that is 4 minus 2.1. I'll go non-calculator one more time and hope for the best. That is 1.9, I hope. And 1.9 is pretty much the upper limit of polarity, right? Before you get to ionic, pretty much, right? So this is going to be a polar bond. And there obviously is degrees of polar bonds, right? This is a pretty polar bond. That fluorine is pretty much pulling those electrons towards it. And again, we could draw our bond dipole, once again, in this case, pointing to the more electronegative atom, and we would point it towards the fluorine at this particular point. Any questions on how to use that? So why don't you do some, are these bonds ionic, polar, or non-polar? If we have, let's do, why don't we do carbon and hydrogen? Why don't we do a little nitrogen and oxygen? Let's do a little sulfur and oxygen for good measure. A little, I don't know, let's do potassium and fluorine. Maybe a little carbon and sulfur. All right, so for each of them, calculate the difference in electronegativity, decide if they're ionic, polar. Okay, so let's take a look and see. We'll start with the carbon hydrogen. So go here. Carbon is 2.5, hydrogen is 2.1, which means if I take the difference in electronegativity, 2.5 minus 2.1, 0.4. That is, again, the upper limit of nonpolar, right? That's really why the upper limit is 0.4 is for the carbon-hydrogen bond, which is the bond you find a lot in organic molecules, which are nonpolar. So that is basically why we cut it off there, not at 0, for example. So carbon-hydrogen would be nonpolar. We'll go nitrogen, which is 3. Oxygen is 3.5. So if we look at our nitrogen oxygen, we basically got our difference in electronegativity of 3.5 minus 3, which is 0.5. That is above 0.4, which means it should be polar in this case. If I was to draw the arrow, it should head towards which one? Nitrogen or oxygen? Should head towards the more electronegative, which would be the oxygen in this case at 3.5. So that is where the bond dipole should go. That means within that bond, the oxygen is more partially negative than the nitrogen in that case. Looking at sulfur and oxygen, sulfur is 2.5 looks like, and oxygen again is 3.5. So we do a little difference in electronegativity here, 3.5 minus 2.5. Going to give us a 1, which is definitely above 0.4 and below 2. So that's going to be a polar bond. In this case, we should draw the arrow pointing towards the oxygen as it is more electronegative in this case. Yeah. Any question on those there? We come to potassium fluorine. I don't even really need the numbers. I should know it's ionic. Yeah. And just to maybe prove it-ish to ourselves, 0.8 and 4, right? So our difference in electronegativity there would be 4 minus 0.8, 3.2. That definitely is above 2. But there are exceptions where you won't get above 2. For example, if you have, say, lithium and say even lithium and sulfur, right? You'll get like a 1 and a 2.5, so you won't really get above 2. So that 2 is sort of a general cutoff, and once again, as long as you see metal, non-metal, you know it's going to be ionic. Now, if we look at carbon and sulfur here, carbon is 2.5, sulfur there is 2.5. That is a difference in electronegativity of 2.5 minus 2.5. That's a 0. Carbon sulfur bond is actually a non-polar bond. Yeah. So it brings up a good point. Definitely, if you have 2 of the same, it's going to be non-polar, right? But it is possible to have 2 different elements that will give you a polar bond. This is what is sometimes referred to as the diagonal relationship on the periodic table. That is carbon. That is sulfur. They're diagonal of each other, not directly diagonal, diagonal over a little bit there to the right. But one is further up, one is further to the right. They cancel out their differences and they end up with the same electronegativity value. Also happens, in a few other places, nitrogen, chlorine as well. Again, diagonal of each other. You'll get some of these relationships where they will actually cancel each other out. Again, not directly below, but kind of over one to the right, you'll get that sort of difference that occurs in a lot of cases, even heading this direction as well. You see some diagonal relationships as well. So again, in most cases, if you have the same elements, it's going to be nonpolar. Also, in most cases, I would say as well, if you have 2 different elements, probably going to be in a lot of cases, especially if they're 2 nonmetals, obviously, will probably be some type of polar bond, but not always, obviously. Now, do you always need the table numbers here to make a pretty good guess? The answer is no, you really don't always need the table. You could use the general trend in electronegativity a lot of times to make a pretty good guess. Again, going up and to the right, more electronegative, down to the left, uh, less electronegative. So for example, if we looked at our nitrogen oxygen, by the way, I didn't really draw that was a polar guy there. I guess I could have drew the dipole heading this way, obviously. Maybe I drew on the bottom there. If we look at our nitrogen oxygen, they're actually in the same period on the periodic table, right? That means oxygen is further to the right, which means it should be more electronegative than nitrogen without even the numbers. Just knowing that, you should have a polar bond if they're in the same row there, basically. The guy further to the right will be more electronegative and will get the arrow drawn towards them. By the way, same deal here, little sulfur oxygen action. They are both in the same group on the periodic table right there. Oxygen is further up in that group, which means it will be more electronegative than the sulfur that's below it, which also will create a polar bond. So if you have 2 elements that are in the same row, are the same group on the periodic table, you don't even need the numbers. It's going to be a polar bond in most cases. And the one that, again, is either further to the right in the same row or further up in the same group will be the more electronegative in that case. So there's a lot of times where you really don't necessarily, again, need the numbers to truly calculate it. You can make a fairly educated guess in a lot of cases as to whether or not you would expect a polar bond or a non-polar bond to form. Again, really in terms of the nonmetals, the only thing you do have to sort of be a little careful of is that sort of diagonal relationship like we saw there with carbon and sulfur or even nitrogen and chlorine. But outside of that, definitely same row, same group, don't need the numbers, just further up or further to the right will probably give you some type of polar bond. Question on how to use electronegativity values to determine bond polarity. This is, again, bond polarity that we're talking about here, where we use the electronegativity values to help us determine that. Again, it's not really telling us in any case, is the molecule polar or nonpolar? I will say the exception to that sentence is the only time that the bond polarity and the molecular polarity will actually be the same, whether or not, that individual bond's polar or nonpolar and the molecule is polar or nonpolar is in a case like we have actually here and here, right? So for example, if we look at each of these guys as we just did, we know that this FF bond, right, is nonpolar. And in that particular molecule, how many bonds are there? That's not a trick question. Yes, there's only one bond, as we just identified it as being nonpolar, which means because this molecule actually only contains one bond, the molecule itself will also be nonpolar. So that is a case where the molecular polarity and the bond polarity will be exactly the same. Because it's a diatomic molecule, it has only one bond. And if that bond's nonpolar, then that means the molecule itself has to be nonpolar. Same thing applies here. This HF bond is polar. And once again, in HF, there is only that bond. There's only one bond, which means if you only have one bond in the molecule and that one bond's polar, then the molecule will be polar as well. So again, there, the molecular polarity and the bond polarity will be the same. They both would be polar. This would act as both the bond dipole and also its dipole moment, as I talked about a second ago, which would indicate that it is a polar molecule as well. We looked at water just briefly to answer that question earlier. When we get to molecules like water or any molecule that has 3 or more atoms, there's a little bit more you have to take into consideration than what we just did here. So this is the only place where, again, both the bond polarity and molecular polarity will definitely be the same. And that's only because it has one bond that makes up the molecule. So whatever it is, it will be. But again, if you get into anything that is 3 or more atoms, there's a few other things you have to look at, and we will talk about that in chapter 4, what things you need to look at to kind of help you determine that. Any questions on that there? All right. Another electronegativity scale, in case you didn't like the other one, I suppose, right? All right. So again, here's sort of the breakdown one more time for sort of, is it a polar, nonpolar, or ionic bond? And I would say nowadays people don't really talk too much about this, but they still sometimes will classify bonds as percent ionic character. And obviously, if you have 100% ionic character, you got an ionic bond happening. Yeah. And obviously, if you're more towards the zero side, you probably have a pure covalent type bond happening, more sharing of electrons. I would say very rarely people speak of percent ionic character. It's usually like a blurb sentence in the chapter or something like that. But sometimes it does still pop up. Most people look at electronegativity values, difference in electronegativity values, and talk about bonds in terms of it either being polar, nonpolar, or sort of ionic. So as we saw there, atoms with really widely different electronegativities will tend to form ionic bonds. Because of that difference in electronegativity, you pretty much have somebody that is not looking to bring electrons to itself and somebody that really wants electrons. So that's enough to kind of pull those electrons away from the metal to the nonmetal. And obviously, when we get into our two nonmetals together, which is our covalent bonding, everybody's in the same location-ish on the periodic table, which means they all have relatively good electronegativity values. And again, we're going to either get equal sharing or some unequal sharing of those electrons. All right. And again, that's why these are basically the breakdown of the two types of bonding. All right, so as I mentioned a second ago, again, that 2 for the ionic really isn't a super fixed number. Again, I would look, like I mentioned, more metal, non-metal, ionic, and rather than the numbers. All right. So now that we've talked about sort of how electrons are shared in a covalent situation, we're going to get to drawing actual Lewis structures and how to draw proper Lewis structures for covalent bonding and the steps that you should follow to frankly draw a good structure, probably. If you follow these steps, you will probably lead you to a pretty good structure. If you do not follow these steps, you probably will lead yourself to a bad structure, maybe, I would say. What a lot of people do that is sometimes bad in a sense when they go to draw the Lewis structures is They oftentimes think of, for example, electrons belonging to a particular element, like this guy starts with this many electrons, this guy starts with this many electrons, how many electrons do they kind of need to get and all that kind of stuff. So I call that kind of drawing Lewis structures by piecework, where you're just kind of taking every individual little element and trying to figure out, how all the electrons go together. Works much better for ionic bonding like we did previously, but for covalent bonding, you really don't want to do that. You want to think of really the electrons as not necessarily belonging to a particular element or atom, but that you have a certain number of electrons and you want to sort of equally distribute those electrons the best that you can over all the atoms that are present in a molecule. So the first thing that you really want to sort of figure out, if you're not sure of, is what is sometimes referred to as what is the skeletal structure. Basically, how are all these atoms going to kind of come together? How are they all connected? And usually, I would say that if you have like one element, an atom of one element, and like three of another, usually that one guy's in the middle and everybody's attached to the middle guy. There are some rules to help you follow to determine what should go where. In general, the least electronegative atom should be in the center. So the one that is the least electronegative atom should be in the center. And again, in a lot of cases of what we draw in this class, a lot of times everybody's just going to be kind of connected to that guy. Not always. There's definitely a lot of molecules where there's multiple central atoms, but a lot of stuff that we come across has kind of like one and everybody's attached to it. Hydrogen and fluorine should never occupy the center for two very important reasons. First off, hydrogen should have how many electrons? Only two, right? The duet rule, which means if you stick hydrogen in the middle, now you're getting to that point where you need to put a big X right over your paper, right? As you got too many bonds to hydrogen, right? Too many dots and those type of things. The second is here, fluorine is the most electronegative atom, which means it should not be in the middle ever, right? Because only the least electronegative atom should be there. So once again, hydrogen on the outside is pretty much what it's going to look like. Again, no dots or anything like that. Probably the more important thing, once you sort of figure out how it's arranged, is counting up the total number of valence electrons there are in the entire molecule or ion or whatever you're drawing. That number is really, really important because you need to have exactly that number once your picture is drawn. You can't have any more, you can't have any less. You got to hit that number on the nose. Now, you may draw something that is a ion, like a polyatomic ion, and that means that you do have to adjust your electron count for the charge. So a reminder that if something has a negative charge, that means it has gained electrons. So you actually need to add to the total number of valence electrons. And if something has they both say negative, right? That one should be positive, I think. There we go. So if you have a positive charge on a cation, which is what that would be, I suppose, that means it has lost electrons, right? So it has lost electrons. So you do need to subtract that from your total there. Once again, the number of valence electrons is pretty much the important number, as you need to basically have a picture with those exact amount of electrons. This is what I was talking about a second ago. Those total electrons, again, you shouldn't think of as like belonging to anybody. We're just going to try to distribute all those electrons to everybody in our picture. Now, once you have the total number of valence electrons, you have a pretty good idea of how it's put together. You then want to make one single bond from the guy in the center to all of the outside atoms. Just a nice single bond. Each single bond represents 2 electrons, right? So you want to count up how many single bonds. By the way, I didn't say double bonds or triple bonds. Once again, you should not be double bonding or triple bonding right out of the box unless you probably want to draw the wrong picture. So again, start with single bonds here. to the outside atoms, you will have a certain amount of electrons still left that you need to put on your picture. Any leftover electrons will go on the outside atoms as pairs of electrons, so dots of electrons, until each of the outside atoms has 8, right? Our octet rule, which is what everybody wants to get to. So you'll continue around and putting them on, once again, not as single electrons, but as pairs of electrons. Now, once you fill up all of the outside atoms and you still have perhaps some electrons to go, those then would find themselves right here, again, as dots, pairs of electrons. Or if you run out of electrons by the time you fill up everybody, you don't put any dots on the bottom or anything like that. So again, we want to kind of distribute our electrons equally over all of the atoms. And once we're done distributing all of our electrons, it's at that point that you want to go around to all the atoms that are present, and you want to basically determine, do they meet the octet rule, except for obviously hydrogen, which should only have 2. You want to make sure obviously it has 2 as well. It is at that point that if you look and somebody does not meet the octet rule, that is where we start to put double bonds on. So that is the purpose of the double bond. And if all the double bonds doesn't fix the problem, then you move on to triple bonds. And if triple bonds doesn't fix the problem, you did something wrong at that point. Probably triple bonds should probably fix the problem at that point. So you do want to sort of, if you have all of the double bond options, you have more than one double bond option, you want to kind of run through all your double bond options before you go to triple bond. So you kind of want to do it in that order. Start with single bonds, and then if you're not good with octet rule, move to double bonds, try to exhaust all your double bond opportunities, and then if that still doesn't fix it, then go to triple bond basically to do it. At that point, you should have a pretty picture that will hopefully get you all the points. Yes, at that particular point. Any questions on that there? So let's see how this works. So try one myself here with you. All right. So we want to draw the Lewis structure here for NF3. So the first thing we could do is count up the total number of valence electrons here in this molecule. Remember that the number of valence electrons equals the group number. So nitrogen is group 5, so that is 5. There are 3 fluorines, and each one is group 7, so there are 7. I'll move my arrow to 7. That is a lot, but we'll go with 26 valence electrons. I didn't use a calculator. I hope for the best there. So it's 21 and 5, 26 still. At this point, we have basically 1 nitrogen and 3 fluorines. Between nitrogen and fluorine, fluorine is more electronegative. Again, I know that, by the way, just because I should know that. But I also know that because if I look on the periodic table, nitrogen and fluorine are in the same row, and fluorine definitely is further to the right, which means it should be more electronegative in that case. So I'm going to set up the arrangement of my atoms. I'm not drawing any connections or anything at this point. I'm just going to kind of set up a logical arrangement for it. By the way, it does not matter if that's your question. You could put the fluorine on top versus the bottom. It doesn't really matter where you kind of put that third fluorine. Now that I have the logical arrangement, we're going to do 1 single bond, 1, 2, and 3. That is 2, 4, and 6 electrons I have used. So I do a little quick subtraction from my 26. I still got 20 valence electrons to go in my picture. These 20 valence electrons are going to go on the outside atoms first until each outside one has 8, unless obviously an outside one was hydrogen. We wouldn't do that. So that is 2, 4, 6, 8, 10, 12, 14, 16, 18 at this point. I have now filled up all the outside atoms. I have now used a grand total of 18 more electrons. I still have 2 more electrons to go at this point. Those 2 electrons go to the center atom, also as pairs of dots. I have now put on there all 26 electrons. The last thing that we want to do is make sure that everybody is all good. So this fluorine, 2, 4, 6, 8, they're all basically identical. So 2, 4, 6, 8, 2, 4, 6, 8. And if we look at the nitrogen here in the middle, 2, 4, 6, and 8. Everybody has 8 valence electrons. We have exactly 26 electrons on our picture without all the highlighting there. That would be the correct Lewis structure there. Any questions on those steps? Again, those are the steps you want to follow to lead you to a good picture. Again, don't try to do any piecework action or anything like that with covalent bonding and Lewis structures. Any questions? All right, so why don't you draw something? I don't know. No, I don't know. Why don't you draw? Oh, we'll do that one. Why not? Let's do actually we'll do NO3 minus. So why don't you draw a Lewis structure for nitrate there? Okay, so let's take a look here and see. We'll go with nitrogen, which is 5. We got 3 oxygens, so that's going to be 3 times our group 6, where oxygen is. And we do have a negative charge, right? So that's nitrate has a -1 charge. Negative means that it has gained electrons, so we do need to add 1 to that there, so we're not off. 18, 19, 24 valence electrons, I think. So once again here, we look at the periodic table between nitrogen and oxygen. We do not need electronegativity values. They are again in the same row on the periodic table. Oxygen is further to the right, which tells us it's more electronegative. And by the way, we only have 1 nitrogen and 3 oxygen, so might as well throw the 1 guy in the middle. We'll go 1 nitrogen in the middle. We'll oxygen up there, oxygen and oxygen. Once again, we're going to do 1 single bond here to everybody. 1, 2, 3. That is 6 electrons. Whoa, that's like 18, I think. So we got 18 more electrons to go. We'll go 2, 4, 6, 8, 10, 12, 14, 16, 18. At that point, we are out of electrons, right? Is everybody good in this case? Has everybody met the octet rule? Well, oxygen has 2, 4, 6, 8. All the oxygens are the same, right? So they all have 8. Nitrogen, 2, 4, 6. That seems a little short to me, right? So in this particular case, nitrogen is not good as it only has 6 valence electrons. Remember, the whole goal of bonding is for everybody to end up with 8, except for our friend, right, hydrogen, which should not. That means that try not to erase the line or the dot. Let's try that again there. Put our dot back and put our line back. So that means that at this point, we need to fix this, right? So can I just lay up some dots there? I cannot because now I have 26 electrons, which is too many. Again, we can only have 24. So this is the part where I do need to make a double bond. And again, I can make a double bond between any of the oxygens. They're all pretty much identical to each other. Can I just draw a line? I cannot for the same reason. I now have 26, and the oxygen there up on top now has 2, 4, 6, 8, 10 electrons, right? So we do need to try to make a double bond. We can double bond at any of the oxygens. When we make a double bond, or really as well, whenever we make even a triple bond, what we're actually going to be doing is taking a pair of electrons and bringing them in to make that double bond. So here I did it up on top, and that's going to give me a double bonded oxygen up on top. We will still have our single bonded oxygen on the left and right hand side. We will also put a little bracket and a minus around it since it's an ion to make it look pretty and all that good stuff and fancy. Now, when we look at this particular guy, everybody's got still 24 electrons. And now everybody has met the octet rule in this case. So again, 2, 4, 6, 8, 2, 4, 6, 8, oxygen, 2, 4, 6, 8, and our nitrogen now again through the double bonding, 2, 4, 6, and 8. So everybody has met the octet rule. We still maintain the correct number of electrons, and that is the proper way of doing that there. Any questions on that there? Could I have double bonded to the left? I absolutely could have, and it would just look very similar, or just have a double bond over there. We could have also double bonded to the right, and we would have a double bond over there. These are all actually related to each other. And sometimes you'll see this arrow that heads in both directions between all these pictures. This is what is known as a resonance structure. A resonance structure arises in a situation like this because there is more than one Lewis structure that you could draw to sort of describe what's happening with that double bond. Those double bond electrons are what is sometimes referred to as being delocalized, which means at any given point in time, they may be next to any of those oxygens. They're kind of moving around. And that's why one Lewis structure by itself doesn't really adequately describe what's going on. You could actually draw several Lewis structures to describe what is going on. So if you're asked to draw all the resonance structure or all the possible resonance structures, you would want to draw all three. If you're just asked to draw a Lewis structure, one of the three here would be sufficient in this particular case. Any questions on that there? All right, so let's try some here. Let's maybe draw some. Why don't you draw all these Lewis structures? Let's go with NH4 plus. Let's go with SH2. Let's go with CO2. Let's do a little SO2. We'll do the one that's on there, I think, CO3 2 minus. We'll do a little nitrogen as well. That sounds like fun, I suppose, maybe. All right, draw the proper Lewis structures for all these here. What you come up with? It's 4 plus. So we will do our valence electrons. So we got 5 for the nitrogen. There are 4 hydrogens. Each one is 1. Again, here we do have a +1 charge, which means it lost electrons. So we do need to subtract 1 there. So that's going to be 9 minus 1, which is 8 valence electrons. Here, obviously, nitrogen has to go in the middle as hydrogen cannot. So we'll just put a hydrogen around on each side. We'll do a single bond to each one. That is 2, 4, 6, 8. We are done there on that one. A little bracket and a plus. Again, each hydrogen has 2 electrons. The nitrogen has 2, 4, 6, 8 electrons. 2, 4, 6, and 8. So everybody is good. Any questions on that one there? Taking a look at the next one here, a little SH2. Sulfur is group 6. Again, we have 2 hydrogens here, each out 1, which again gives us 8 valence electrons. Once again, hydrogen cannot be in the middle, so it's got to be sulfur in the middle here. A single bond to each gives us 2, 4 electrons, leaves us 4 more to go. Am I going to put any dots on the hydrogen? I am not, because I don't want to get it wrong. So that means really we have nowhere else to go but to the center now. And that is where the dots are going to come. And there we go. And now here, our sulfur has again 2, 4, 6, 8, and each hydrogen has 2 and 2. So it is perfectly fine at that point. Any questions on that one there? Get rid of some of the circles there, maybe. All right, then that rolls us to CO2. CO2, carbon is group 4, oxygen is 6, and there's 2 of them. That's 12, and 4 is 16 valence electrons. In this case, we look at the periodic table and we see carbon and oxygen in the same row, oxygen further to the right, which means it's more electronegative. That means our carbon should be in the middle. Again, we're going to do a single bond. That is 2, 4 electrons. That leaves us 12 more to go. Those are going to go on the outside ones. So 2, 4, 6, that is filled. 8, 10, and 12. At that point, I have now filled all my electrons. Is everybody good in this case? Yeah, carbon is not so good. It has only 2 and 4 electrons. So again, this is a situation where we do need to fix that. We could actually double bond either oxygen. So we could take a pair of electrons and bring it in. And if we do that, we will end up with a double bond here and a single bond here. That still, in this case, does not fix it, right? We're closer now. Carbon now has 2, 4, 6 electrons. We still have an opportunity here to make another double bond on the other side. That is the preferred choice in most cases before you decide you want to make a triple bond. And we will revisit why you wouldn't make a triple bond a little later on in this chapter. But for now, we will exhaust our double bond option by taking a pair of electrons in, and that will give us a double bonded oxygen on each side. And now we will be good. We still have 24 electrons, or 16 electrons, I'm sorry. And our carbon is now going to be perfectly good with its 2, 4, 6, 8. And obviously our oxygen is 2, 4, 6, 8, 2, 4, 6, and 8 on each side. So in this case, we actually needed 2 double bonds to allow everybody to get to that octet rule. Any questions on that there? Okay, we'll save the other 3 for next time, and we'll start with those. We will lay it up.